Hello, as we start talking about enzyme catalysis, we are going to see that transition state theory is a key idea. This is the idea that enzymes bind more tightly to the transition state than the starting substrate. If we look at a reaction progress diagram, we start with the enzyme plus the substrate. They have to come together to form the enzyme substrate complex. Then the reaction occurs and we have an enzyme product complex. And then we have to let go and the enzyme releases the product. If we stabilize the transition state of the enzyme substrate reaction and decrease that energy, we see that this reaction is an easier set of hills to go over, an easier pathway. However, there's an idea that it seems to make sense sometimes that if we stabilize or bind tightly to the substrate, but in reality what happens then is that the barrier to get over that reaction now is tremendously high. So what we really want to do is reduce the height of that barrier for the reaction. And stabilizing the product similarly makes this barrier to letting go of the products too high. So we really want to stabilize that transition state. Built on that then is the idea that if I want to inhibit that enzyme, I need to make a drug that will bind tightly to the enzyme active site. And so we know that the transition state binds the tightest. My new drug will also need to bind very tightly and will probably need to resemble the transition state. So an example here is the hydrolysis of a protein by the enzyme thermolysin. So the hydrolysis of this amide bond occurs in the enzyme. Water attacks here, and really the transition state is, remember, the making of this new bond and the breaking of this bond. So we can say it probably looks something like this short-lived intermediate, even though this already has the products made. So I started with a trigonal planar amide. My transition state or intermediate will be tetrahedral with a minus charge or developing negative charge on one of the oxygens. This then pi donates down and kicks off the nitrogen, giving me the carboxylic acid and the amine. So the inhibitor for this enzyme, it turns out, is this structure. And if you look at it, especially if you remember that this phosphate is often represented as O minus and 4 bonds with a plus on the phosphorus, you can see that this looks an awful lot like this tetrahedral transition state with the nitrogen, an OH, an O minus on a tetrahedral. It's a phosphorus instead of a carbon, but we have similar charges and similar geometry to the transition state and geometry. So those are going to be things that we look for, not a resemblance to the starting material, but a resemblance to that transition state. And the resemblance needs to look like it in geometry and electronics. So inhibitors which resemble the transition state structure will bind more tightly to the enzyme than the actual substrate.